So I keep underestimating how long problems are going to take me, and I get cut off, which is fine. We just pick up where we left off. So last time we got cut off in the middle of part C here. We were calculating the pH at the equilibrium point, which we technically don't even have to do for this problem, because for a strong acid and a strong base, the pH at the equilibrium point is always going to be 7, because the definition at the equilibrium point is that the moles of hydrogen are going to equal the moles of hydroxide. And so when that happens, that is the definition of a pH of 7, because when that happens, the pH is simply the pH of water. What we have, all of those ions have, there's no excess of hydrogen or hydroxide. They are equal. That is the definition of water and a neutral pH. So the pH at the equivalence point is going to be 7.00. All right, part D, it asks us to calculate the pH after adding 30 mils of HNO3. All right, so let's figure out where that is at. Is that going to be before equilibrium or after equilibrium? We don't know what the volume is at equilibrium. We didn't calculate that. Oh yeah, we did. Okay, so in part B, we calculated the volume of acid needed to reach the equilibrium point is 66.7 milliliters. So 30 milliliters is going to be before the equilibrium. So we're going to expect it to still be pretty basic. But let's do that calculation. So how many moles of hydroxide do we have, and how many moles of hydrogen do we have at that point? So we have a defined amount of the base, which is 50 milliliters, and I want to make that, let me do it this way. Let's do the concentration, which is 0.200 molar, or moles per liter, times the volume, 50 milliliters, but I want it in liters, 0.05 liters. That gives us the moles, so 0.2 whatever, I'm doing the math myself here, times 0.05. I'm going to get my decimals wrong if I don't do this on a calculator, even though I should be able to do this in my head. 0.2 times 0.05 is 0.01 moles of hydroxide. And the moles of hydrogen ion, we have a 0.150 molar, or moles per liter, of acid. And in this part, it asks after we've added 30 milliliters, so that's 0.3 liters. So that is 0.15 times 0.03, 0.0045 moles of hydrogen. So that means we have an excess of OH. If we do some subtraction here, 0.01 minus 0.0045, we get an excess of 0.0055 moles of hydroxide. All right, that's the number of moles. But to get the concentration of hydroxide, we need moles per liter. So 0.0055 moles divided by the concentration, or sorry, the volume in liters. The volume, so this is, over here we've calculated the moles, and over here, these are the volumes that we added. So 0.05 plus 0.03 is 0.08 liters is our total volume. And so our concentration of hydroxide is 0.0055 divided by 0.08, which is 0.06875 moles per liter, or molarity. So the pH, since this is hydroxide, we're going to find the pOH, take the negative log of that number, and that is 1.16. So the pH is 14 minus 1.16, which is 12.84. So if we pencil that in up here, 12.84 0.84, and we check that makes sense because the initial pH was 13.30, and we did add some acid, so we would expect the pH to go down, and it did, but just a little bit, because that's the pattern that we see with strong acid, strong base titration. All right, you still should have some space on the next page, hopefully. I'm just going to keep erasing and doing all the problems right here. So part E, moving on to part E, calculate the pH now after adding 100 milliliters of acid. Well, that's going to be past the titration point past the equivalence point, since the equivalence point happens at 66.7 milliliters. So in this case, we expect to have an excess of hydrogen, of acid. So again, we're just going through the steps. We're figuring out how many moles of hydroxide and how many moles of hydrogen we have. So the moles of hydroxide are not changing. We have a fixed volume and concentration. So what we calculated in the previous problem was that we had, now I can't even remember, 0.01 moles of hydroxide, right? 0.05 times 0.05 times 0.2 is 0.01 moles of hydroxide. Okay, so if that's how many moles of hydroxide we have, in this case we have a new volume, or a new number of moles of H plus, because we're adding a different volume. So we still have the concentration of 0.15 molar, or moles per liter, times our new volume of 100 milliliters, or 0.1 liter, gives us 0.015 moles of hydrogen. So 0.015 minus 0.01, that we are going to neutralize all of that hydrogen, all of that hydroxide, and we're going to have left over 0.005 moles of H plus at this point. Did I do that wrong? 0.015 minus 0.01. Nope, I did that right. Okay, so now the pH at this point is going to be the negative log of the concentration of H plus. This is not the concentration of H plus. This is just the moles of H plus. The concentration is the moles per liter. So the total volume that we have at this point is the 50 milliliters of base plus the 100 milliliters of acid that we added. So that's 150 milliliters, or 0.150 liters. So the concentration of H plus is 0.005 divided by 0.15, or in other words, 0.0333, repeating, molar. So the pH is the negative log of that concentration, 0.03333. The negative log is 1.48. So the pH here is 1.48. We expect it to be very acidic because this is well after the equivalence point, like 34 milliliters beyond that equivalence point. All right, and then lastly, part F, it asks us to sketch a titration curve based on all these values. So let's do that. All right, so here is our axis. The titrant that we're adding goes down here. So this is going to be volume of HNO3. In this case, this is the acid that we're adding. And this is the pH on the y-axis. All right, so let's say, I'm just going to make some tick marks here. Let's call this a pH of 7 because it's in the middle. 5, 3, well, I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so it's not really to scale, but I have tick marks for the whole pH scale. All right, and then here's my volumes. And we are going from 0 to 100 milliliters. So I probably should count my tick marks. 2, 3, 4, 5, 6, 7, 8. Whatever, we'll just extend this. So there's my 100 milliliters, and these are 10 milliliter tick marks. Alrighty, not the prettiest graph, but it does say sketch. Just sketch it. Okay, so at the start, at 0, the initial A here, the initial pH is 13.3. So I'll put right here is my initial pH at 13.3. And then, and that's at 0 milliliters. Now at 66.7 is where the equivalence point is. So 10, 20, 30, 40, 50, 60, 70. So somewhere in here is where we reach the pH of 7, our equivalence point. And then at 100 milliliters, that's part E, I have a pH of 1.48. So something like here. And at 30 milliliters, a pH of 12.84. All right, so my titration curve is going to look something like this, steep drop, and then like this. All right, so there's the titration curve where I've got my equivalence point at roughly 66.7 milliliters, my starting initial pH, and then the pH down here where I guess I should just carry it to that point. Okay, so that is multiple part titration problem. Took us a lot of time to go through all the parts, but really we just did 6 different problems given the same amount of information. So this is, again, all for a strong acid and strong base. But now we're going to talk about the titration curves, which look slightly different for if you have a weak acid and a strong base, or a weak base and a strong acid. So let's go to page 7 of the notes. All right, and here we find the notes on a weak acid and strong base titration. And this is what you're going to be doing in your lab this week. You're going to be using acetic acid, vinegar, which is a weak acid, and sodium hydroxide, which is a strong base. So this curve will be particularly relevant to you. Alrighty, so some differences in this titration curve. So the initial pH of the weak acid solution is going to be found slightly differently. So for a weak acid, the initial pH is found using an icebox because weak acids are only partially dissociating. So for example, in this problem, we are starting with 0.1 molar, 25 milliliters of a 0.1 molar solution. So to figure out the concentration of hydrogen and the pH, we've got to use an icebox. HCHO2 will partially dissociate into H plus and CHO2 minus. And if we make an icebox, initially we have a concentration of 0.1 molar, 0 and 0. These will go down, the products will go up by X, and so at equilibrium we'll have a concentration of 0.1 minus X, X, and X. We can look up the Ka for this acid on the table, and we find that it is 1.8 times 10 to the negative 4. This is still pretty small, so we can use the X approximation technique when we solve this problem. 1.8 times 10 to the negative 4 equals products, so X times X, or X squared, divided by 0.1 minus X. If we use the X approximation technique, that will greatly simplify solving this problem. Multiply both sides by 0.1, take the square root of both sides, and we get x equals 0.00424. We need to check this. Is it less than 5% of the initial concentration? 0.00424 divided by 0.1 molar times 100% is 4.2%. So yes, this is valid. Alrighty, so that means that X is our concentration of hydrogen at this equilibrium for this concentration. So 0.00424 molar is our concentration. So therefore our pH is the negative log of that. And the negative log of that is 2.37. All right, so we can mark that here on our titration. The initial pH is, let's call this 2.37 right here. Right, so not quite as acidic before because this is a weak acid. So a 0.1 molar solution of a weak acid is not going to have as low a pH as a 0.1 molar solution of a strong acid because it doesn't have as high of a concentration of hydrogen ions. Okay, so next part is finding the okay, so this is the rising part. So here's the initial concentration, and then to find the concentration at any point between there and the equivalence point, all right, we use a different formula. So before we just figured out for a strong acid, strong base, we just did some subtraction. We figured out how many moles of acid and how many moles of base we had, and whichever one was in excess, we figured that out. But the interesting thing with a weak acid and strong base is that in this zone here, it has a slightly different shape because what happens is it acts as a buffer. There's sort of a buffering capacity in this stage. All right, so in order to figure out the pH, we have to use the Henderson-Hasselbalch equation, which is the equation that we use for buffers, the pH of buffers. So let's do an example. All right, let's calculate the pH. If we add 5 milliliters of NaOH. Okay, so we still need to know the moles of the acid and the base because we need to know the concentration of the acid and base for the Henderson-Hasselbalch equation. So first we'll figure out the moles of the hydroxide. Why not? And that's going to be the concentration of the hydroxide, which on the previous slide we said that NaOH was a 1 molar solution. In other words, there's 1 mole per liter. And if we're adding 5 milliliters, that's just 0.005 liters. Our liters cancel out, and we end up with 0.0005 moles of hydroxide. And the moles of acid, we've got 0.1 moles per liter. It's also 1 molar. And we are using 25 milliliters of the acid if you look at the previous page. So 25 milliliters is 0.025 liters. So we have 0.0025 moles of H+. All right, so if we draw out this equation, HCHO2, all right, our weak acid here, when it reacts with the base that we add to it, it gets neutralized into water, and then we have also the conjugate base of this weak acid. And so these are in equilibrium with each other. All right, so initially we have 0.0025 moles of this acid, and we are neutralizing 0.0005 moles of that acid. And so this is our change, all right? But we are also, if we're losing 0.5 moles of this, that also means that we are gaining 0.005 moles of this conjugate base. All right, so in the end, we have 0.002 moles of this acid and 0.005 moles of this base. So to get for the Henderson-Hasselbalch equation, we need to know the ratio of the concentration of the base over the concentration of the acid. This being the base, the conjugate base, and this being our weak acid. All right, so but to convert these into concentrations, we need to divide by the volume in liters. And the total liters that we had 25 milliliters of the acid, and we added 5 milliliters of base. So we have a total volume of 30 milliliters or 0.03 liters. So the concentration of the acid at this point is 0.0667 molar, and the concentration of the base is 0.0167 molar. So now we have these concentrations that we need to plug in to the Henderson-Hasselbalch equation. So the pH we can now solve for is the pKa plus the log of the concentration of the base over the concentration of the acid. So the pH equals the pKa, which we have to look up. We had the pKa on the previous slide. So the pKa is going to be the negative log of the Ka, and the Ka we said was 1.8 times 10 to the negative 4. So the pKa is 3.74 plus the log of the concentration of the base, which is this, 0.0167 molar, over the concentration of the acid, 0.0667 molar, and that comes out to a pH of 3.14. The log of this fraction is negative 0.601. So it's 3.74 minus 0.601, and that equals a pH of 3.14. All right, so if we go back real quick to this page, after we've added 5 milliliters, we have a pH of 3.14. So the shape of this curve that we're going to see is kind of unique. So with a strong acid and a strong base, we saw this sort of flat line up until the equivalence point, but with a weak acid and a strong base, it's sort of a weird line. That's the buffering capacity that we see, all right, until the equivalence point. And another thing that we're going to see with the next problem is that the equivalence point, notice that I've drawn this dot, although I've drawn it very big, it's greater than a pH of 7. All right? So because it's a weak acid, when we add an equal amount of base to that acid, it's actually going to be a slightly higher than pH 7 pH because that acid is very weak. All right, and we'll show you the math for that in part 3. Part 3 here, at the equivalence point, all of the weak acid has been converted to conjugate base, And so the pH is going to be determined by the concentration of the weak base. Okay, we're using the same equation here, that at the equivalence point, we have used up all of this acid has been neutralized and has therefore become the weak base. And that weak base is slightly basic, hence the slightly basic pH at the equivalence point. So if we calculate here the volume of NaOH, let's calculate the volume of NaOH and the pH at the equivalence point. All right, so for the equivalence point, to calculate the volume, we're always using this equation. So the molarity of the acid times the volume of the acid equals molarity of the base times the volume of the base. Well, the acid, we're told, has a molarity of 0.1 molar, and we have a starting volume of 25 milliliters. And the molarity of the base is 0.1 molar, and so the volume of the base, if we solve this, is going to be 25 milliliters of NaOH. Okay? But it's not going to be neutral. And that is because so let's figure out how many moles we have first of all. So at the equivalence point, we have the same number of moles of acid as we do of base. That's the definition of the equivalence point. So let's figure out one of these. So the moles of acid, we have 0.1 moles per liter times 0.025 liters. And as we've seen before, that means that we have 0.0025 moles. So at equilibrium, at the equivalence point, we have 0.0025 moles of each, the acid and the base that we've added. But because it's a weak acid, HCO2, all right, if we neutralize, all right, 0.0025 moles of this, it means that we create I didn't quite write this out. HCHO. All right, so that's the correct formula. That means that we add 0.0025 moles of this. All right, we went down, we reduced this by 0.0025, which means that we gained 0.0025 moles of this base. All right, so in order to figure out the pH, we need to figure out the pH of this. All right. And so we need to write out an ice box. We need to write the equation and figure out an ice box for this. So I'll do that on the next page, and I think I have just enough time to do this. So this weak base, CH2, plus water is going to react to form HCHO2 plus OH minus. And the Kb for this base is 5.6 times 10 to the negative fourth. So initial change equilibrium, we just said that we have 0.025 moles, all right, but we need concentration, and the total concentration at this point, we've added 25 mils of base to our 25 mils of acid, so that's a total of 50 mils or 0.05 liters. All right, and this is going to go, this is change equilibrium. This will go down by X, and this one is the one we care about, will go up by X. And so at equilibrium, this concentration, by the way, 0.025, screw it, I'm not gonna be able to finish this in time. We will do this problem in the next video.